In this video, we'll walk through some activities, some examples of counting. So we'll find how many different ways we can do a few different things, like building a pizza, forming a committee, arranging books, creating a 7-digit phone number, etc. Here's the activity sheet, and if you don't already have the activity printed out, you may want to have it printed out for this example, or if you have a second device, pull up the activity sheet on that second device and then follow along in the video. But part of the video, the activity sheet might be a little bit too small to read really well, depending on your eyesight and the device you're reading from. But let's get started here. How many different one-topping vegetable pizzas can be made? If Pizza King offers 3 meats, ham, pepperoni, and sausage, and it looks like 4 vegetables, then one-topping pizzas with vegetables, it looks like there's 4. We're not going to include the no toppings, right? Because it's one topping. And we could list them as onion, peppers, mushrooms, and olives. You could write those out. I'm just going to use an abbreviation for each of those. How many different 2-topping vegetable pizzas can be made? Well, here's where we're going to apply a little bit of the counting principle. And there's 2 ways we could do this. So to start with, if we were thinking through putting toppings on a pizza, it doesn't matter which of the vegetables we put first, it'd be the same. So this is a combination. It's not a permutation. A permutation is where we have an ordered arrangement, but a combination of 4 different toppings selected 2 at a time. The formula for a combination of n items selected r at a time is n factorial divided by n minus r factorial times r factorial. There's our formula. But this one could also be done with just the fundamental counting. So we're going to say how many different ways can I combine each of the different. If I were to just start listing the options, if I started with onion, we could have onion and pepper, onion and mushroom, or onion and olives. Now, those are all the combinations using onions because we're not using a double onion as an option. And then when I move to starting with peppers, we could have peppers and mushrooms or peppers and olives. Notice peppers and onions is already counted, right? And then if the first topping is mushrooms, then I could have olives. So it looks like there's 1, 2, 3, 4, 5, 6 different ways to do this. But let's do this with the formula also. This would be a combination of 4 vegetables chosen 2 at a time. So that's going to be 4 factorial divided by 2 factorial times 4 minus 2, or 2 again, factorial. So 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. I could do this without a calculator because 2 times 2 is 4, and we're left with 3 times 2, or 6. So we get the same answer there either way. How about one-topping meat pizzas? There's 3 meats to choose from. And if I listed them all, we'd have ham, pepperoni, or sausage. If I wanted to put 2 of them together, ham and pepperoni, or ham and sausage, or pepperoni and sausage. If I did this as a combination, the combination of 3 toppings, chosen 2 at a time, would be 3 factorial over 2 factorial, 1 factorial. So 3 times 2 times 1 over 2 times 1 times 1. If I reduce the 2, it looks like we're left with 3 times 1 over 1, or 3. So we get that 3 either way. How many different pizzas can be made with 1 meat and 1 vegetable? Now we're getting tricky here, right? Here's how I would approach this using the fundamental counting principle. How many ways can we choose a meat? And then multiply that by how many ways can we choose a vegetable? We can choose from 3 different meats and 4 different vegetables. So there's 3 ways to choose a meat, 4 ways to choose a vegetable. 3 times 4 gives us 12 different pizzas. If I were to list them, I'm going to find this easiest to do with a chart, a tree diagram. Do you see how I use this tree diagram? Starting with ham, I could then add onions, peppers, mushrooms, or olives. Starting with pepperoni, we could then add onions, peppers, mushrooms, or olives. Starting with sausage, onions, peppers, mushrooms, or olives. So the list of the 12 different options are here. Ham and onions, etc. And then how many different pizzas can be made with 2 meats and 2 vegetables? Now this is going to get to be quite a bit more, so I'm not going to do a tree diagram for this, and I'm not going to list them. I'm just going to use the counting principle. So if I were to look for 2 meats, how many different ways can I choose 2 meats? And multiply that by 2 vegetables. How many different ways can I choose 2 vegetables? I already worked out that there were 3 2 meat pizzas possible, and that I already found that there's 6 ways to put on 2 vegetables. So if I multiply 3 times 6, I'm going to get that there are 18 different pizzas that can be made with 2 meats and 2 vegetables. And notice I'm not going to list all of those. Let's move to the next part. Count each of the following: the number of 4-people committees, the number of selections of 3 people from 20, 10 students in English have a book and they pick out of the hat how many different student book selections are possible, and then the Burger Boy restaurant with employees. We want to know how many different committees can be formed. Well, for each of these, here's the first step. The first step is to determine, is it a combination or is it a permutation? It takes a little bit of practice, but here's the big key, is that if it's an ordered arrangement, then it's a permutation. And the big key here is, does the order matter? So if we talk about a number of 4-people committees from 25 people, does it matter which order those people are chosen from? No, it doesn't matter what order we choose the people when we're making a committee, whether you're the first one chosen or whether you're the last one chosen, you're a member of the committee. So we have a combination, not a permutation, of 25 people selected 4 at a time. So using the formula, so applying the formula, we would have 25 factorial divided by 4 factorial times 21 factorial, so 25 minus 4. And also, did you know you can put that in directly to your scientific calculator? If you have the probability key on your calculator, I'm using a Texas Instruments 30X, and there's a PRB in the second row of buttons. When you hit that PRB, it gives you NPR or NCR. I'm gonna, to type this combination of 25, choose 4. I'm gonna type in 25, and then I'm gonna type in PRB, and I'm gonna arrow over to select NCR, and then I'm gonna type in 4, And then I'm going to choose enter, and I get the result of 12,650 different committees. Look at that. If you only had 25 people and you're making a committee of 4, there are 12,650 different committees we could make. Now for part B, the number of selections of 3 people from 20. If the first is in charge of the main course, the second is in charge of the salad, the third is in charge of the dessert. So we've got different people, 3 different people who are going to work to create a menu. And do you notice that the order is going to matter for this example? So now for part B, we've got a permutation of 20 people chosen 3 at a time. So when I put that in to the calculator, I could use the formula, 20 factorial over 17 factorial, or I could put it directly into the calculator, but I'm going to get 6,840. And then for part C, 10 students in English class are given a book to read, and based on the number that they picked out of a hat. How many different ways can we pick that number out of the hat? Well, all 10 are going to pick a number. So this one's interesting. We could do this. We could do this with a permutation. 10 students, 10 at a time, but it's going to be the same thing as 10 factorial. So if there's 10 students to choose from for the first pick, and then there's 9 left, 8 left, 7 left, etc. Do you see that that's the same as 10 factorial? So either way, we're going to get the same number, and I'm going to leave that for you to put into your calculator to show that you can do that. Part D is a little bit different because we've got 2 different things. We've got 2 combinations going on at once. So Burger Boy has 10 men and 12 women, and there's going to be a committee of 2 men and 2 women. So with it being a committee, it's a combination. So we have a combination of 10 men chosen 2 at a time, and then we're going to multiply that times the different ways that we could build the committee of women. 12 women chosen 2 at a time. So when I put those into the calculator, I get 45 committee of men times 66 different options for the committees of women. So that comes to 2,970. 2,970. I'm going to end the video here, but if you'd like to continue with the second half of the sheet, then I will continue number 3 on a next video, but we'll end here to make it nice and short and concise. Please reach out to me if you need more help with any of these first examples. Happy to help you with more examples or with more detail.